Good afternoon, everyone, and thank you very much for coming to my talk. I'm going to present to you a paper that I'm going to present in MICI in a few months. Its name is Deeper Image Quality Transfer, Training Low Memory Neural Networks for 3D Images. And I would like to start by thanking my collaborators, one of whom is in this room. So, what's the overview of today's presentation? I'm first going to give an introduction to the clinical background that we applied this neural network, this low memory technique to, which is image quality transfer. I'm then going to describe in detail how you would augment a neural network to create a low memory system, or how you would implement it in a neural network in any case. And then finally, I'm going to conclude briefly to talk about my current work. So, what is image quality transfer? It's this idea that you can transfer information from high-quality scans to low-quality scans. So the idea is you obtain training data from a group of subjects by scanning them with low-quality scanners and high-quality scanners, learn a mapping between them, and then eventually deploy the low-quality scanners in places where they might not have access to high-quality scanners, which is the majority of the developing world, and in fact also most of the Western world. So far, there have been 4 IQT papers. The first 3 learned this previous mapping by using random forest regression. And then the 4th one, which also won the Paper of the Year award at last year's MICI, introduced convolutional neural networks to this task. And this was done by my colleague who is not here today. So, what is the problem that we face in medical image computing? Well, whilst deeper networks are better, or they're more easily or more readily optimized, they require more memory to train. How so? Well, when computing the forward pass in a neural network, you often have to cache, or save to the memory, intermediate activations. So if you have a bigger network here, you will end up having to cache more values. And this can quickly produce memory bottlenecks in our situation, because most of deep learning is performed on GPU, or the training, which have limited memory. At the moment, we're using 12 gigabyte cards, and the current state of the art is 24, I believe, if you're not Google DeepMind or one of these big companies. And this is a particular problem for us, because our data is frequently 3-dimensional because of the human body, multi-channeled because we're not simply measuring standard colors, and it often has high resolution. And this presents a problem when you want to have large inputs to a neural network. So what usually happens is people train with, for example, mini batch sizes of 1, or use very small inputs, which can only capture localized information. So the aim of this paper was the idea of augmenting the ESPCM, which is this network, which was the network used in our previous IQT paper, and to see if we could produce better results in Fusion MRI super resolution without increasing the memory usage. And our plan was to combine 2 techniques called checkpointing with reversible networks. So I'm going to start talking about reversible networks by introducing their previous incarnation, which is what's called a residual network. And the idea here is that you have an input, and the output is a sum of the input with this convolutional layer, which is necessary to do the deep learning vision process that we need. And the idea is here, this connection here acts as like an earth wire. So if there's a problem with training, then the information of the neural network will flow through here, meaning that we will not obtain problems in training, which often happens. And in fact, the residual network, which was this enormous layer, obtained state-of-the-art results a few years ago, simply by being able to stack many of these one after each other. The reversible networks was introduced more or less in 3 equivalent papers, or at the same time. And it's very similar to the residual block, with the augmentation that you can also pass the information backwards from the output of the layer to the input. So this is the forward pass, and this is the backwards pass of a reversible block. Sorry. So if you remember what a residual block is, having this convolutional layers F, the reversible block now has 2 of these convolutional layers, which are nonlinear functions that are used throughout all of computer vision. And whilst the residual block has this earthwire identity function, the reversible block now has two of these identity functions, or earthwires, on the top and the bottom. These red lines here correspond to splitting up and concatenating the input feature space, often along the channel dimension. And so the idea is you have an input, you split it along the channels, then you perform this transformation, and then you concatenate at the end. And this allows us to do a forward and backwards pass through each reversible block. Now, why is this useful? Well, suppose that we stack reversible blocks instead of residual blocks. In the forward pass, instead of caching intermediate activations, we would cache absolutely nothing. When we obtain the loss gradient at the end, and also the final activations, and we wish to propagate backwards, we would do this iteratively by reversible block. So at stage B1 here, we would have the loss gradient and the activations. We would pass these two values backwards throughout the reversible block, and at the same time, we would calculate the intermediate gradients. We would perform the optimization step, and then we would delete all unnecessary values. At stage B2, we now have the loss gradient and the activations. And again, we would pass these, due to the reversible properties of the reversible block, to B3, whilst calculating the loss gradients in between B2 and B3. We would then delete all unnecessary values afterwards. So on, so on, and so on, and so on. And the idea is, at any point, you only need to contain the information between one of these two blocks in the memory. So the input and the output, which are of course shared in consecutive blocks. One reason why this is useful is that we can simply take an optimized architecture and extend it with these reversible blocks. So if we take two layers of any neural network, split the intermediate activations, we can simply insert reversible blocks between them. So here we've stocked R blocks in a single stack. And the idea is we want to augment a neural network and improve its predictive power. So for the purposes of this paper, we took the ESPCN, which is my colleague's network, and then we augmented it by adding a stack before each one of the layers. The global forward and backward propagation was done in a similar fashion to how I previously described the iterative procedure. In the forward pass, we cache absolutely nothing except for 3 intermediate activations. In the backwards pass, which is illustrated here for the region between A2 and A1, we do this procedure that I described before on the reversible blocks, on the reversible block. And then we would also do a backpropagation procedure on the non-reversible layer, which is in this case the ESPCN second layer. So this procedure would be repeated 3 times, well 2 times, and then this in this network. What I would just like to point out is here we're saving 3 activations because in effect we have split this whole network up into 4. And I'll come on to that in a bit. So here are our results. The previous best results in my colleague's paper were here. The number after this Rn signifies how many blocks are in a single stack. So 4 here would mean that there are 4 blocks before each layer. So effectively it would be 4 times longer, hypothetically. And we can see that we're able to produce much better results whilst keeping the memory roughly constant. So this was the original network, and this was our augmenting network with the low memory system. To make a fair comparison of our memory saving technique, we compared our low memory system with its naive implementation, which is effectively, if we ignored the reversibility property and also didn't do this checkpointing procedure, but took a single computational graph from the input to the output and then performed backward propagation on the whole network, which is what people do in medical imaging and computer vision, we would need much more memory. In fact, twice as much, approximately. The cost of this is, of course, an increase of computational time. However, we can see that the increase in computational time was much less than the memory saved. And in addition, it is often the memory that is the bottleneck in medical image computing. And we'd also like to point out again that this network here is about 4 times bigger than this network here. A brief image comparison. Here we would have the low resolution input, let's say from a low quality scanner. We would have the high resolution output, let's say from a high quality scanner. And here is a visual comparison between our state-of-the-art results and the previous. And you can see that there are some visual differences. So how can we apply this to other neural networks? Well, what we did was we effectively divided our elongated neural network into 4, represented by these magenta ellipses. And in the forward pass, we would save the activations in between the magenta ellipses. And in the backwards propagation, we effectively consider these all to be separate networks and passed the gradient backwards and also the activations from network to network. So this is possible in our network here, and also possible, let's say, in a dense implementation of our network, which can save a considerable amount of memory. Here's another slightly more horrible-looking example. It's the inception network. It is comprised of inception blocks, which are repeated, and also some detector offshoots, which make predictions. Now, with our methodology, the user can choose how he wishes to divide this network. And he can also choose whether he wants to add reversible blocks to the end of these subnetworks. So in this scenario, we have divided it into more networks than here, which means more or less that this would take more time to train, but would conserve more memory. But the message of our paper is that we can in effect control the memory usage whilst trading it off with computational time. And whilst our clinical application was super resolution, we can also apply this technique to other techniques in medical imaging, such as image segmentation, synthesis, registration, or in fact anything to do with deep learning. So if you're interested with the system, please get in touch. Or if you want some more information about how to implement it. So our work at the moment in the IQT group is based on these 3 things. The first one is this idea of data harmonization, which is that you obtain different scans from the same person under different clinical settings. And we want to see if you can use machine learning to map information from these different scans. And this is very important clinically, as often patients are scanned with slightly different settings in different hospitals. So we want to harmonize the data. We want the neural network to be able to transfer its information from one scan to the other. The second project is trying to speed up these 3D convolutions, so convolutions on 3D data. As you saw, our methodology does slow down quite considerably, the training quite considerably, but there are methods that have been implemented to try and speed this process up, and we're trying to apply this in a medical imaging setting. And the final project is the idea that we want to grow a neural network. So we start by either training a small neural network or by using someone else's trained results and then augmenting it slowly, saving a huge amount of computational time. I'd like to conclude by thanking these people who helped considerably with the writing and submission of the paper. Thank you very much.